Okay, I'm going to start. See, I have sound. It is recording, so we're in good shape. So I'm going to go ahead and get started with talking about today's stuff. Let's see. I don't have the thing up because I don't have any pictures to show or anything, so I'm just talking today about the stuff that I got on this sheet, which is mostly. So I'm gonna hopefully finish up everything today. There you go. Thank you. So hopefully I'm going to finish up everything today on Chapter 9, but it might lead on to Friday a little bit. So there is a reading due on Friday. We're going to get into stellar interiors next. So right now we've been talking about stellar atmospheres. So I don't know. This is all messy and confusing. And it's messy and confusing because the system is messy and confusing. So there's a lot of pieces to keep in mind and a lot of things to take into account. So the first thing I'm going to do is just recap for a second and talk about the thing that we've talked about already, optical depth. So what is optical depth? Optical depth is a measure of how much crap is between you and the source. And that crap could be low density stuff that's in a very little sheet, or it could be high density stuff. It could be low density stuff that's this wide or high density stuff that's this wide. You can't tell because the photons went through and some of them got dispersed. So you can't really tell. So we're going to start with the equation of radiative transfer, which says that I of nu di ds equals minus kappa of nu rho, not of nu. Density doesn't depend on frequency. I of nu. And we can solve this. We can solve this integral. Okay, so really, kappa of nu and rho of nu might depend on what? What is the one variable in this equation that kappa and rho might depend on? Rho doesn't depend on frequency, but it does depend on S. It depends on position, where it is. But for the most part, we're going to ignore that. We're just going to say it's roughly constant, because for the most part it is. So as long as I can treat these two guys as constant, then I can solve this, and I get I as a function of nu of S equals I naught, which is the light at the source, e to the minus this stuff in the top, which I'm going to call tau. And tau is the integral from 0 to L of kappa nu rho ds. So tau, okay, let's write this a different way. Let's assume that kappa, wait, what's kappa? Kappa is how big my molecules are, more or less. It's more or less the cross-section per unit mass of the things that are in the way. So what does this equation tell us? This equation tells me that I've got a star. We'll talk about what's in the star next week. Actually, I'm going to move my camera so that it's more centrally situated. Oh, is this going to fail? Okay, so I have this star, and it produces some light, I. Now, okay, maybe it produces a flux, F, if that's what the quantity that you're worried about. Those things, so there are several quantities that we get from doing various integrals of I. Here Q is just one of the integrals that we did. So the flux is one integral, the radiation pressure is another integral, the total internal energy is another integral, right? So you remember reading about all those at the beginning of the chapter. They're just integrals of Q. So if I integrate Q, I can integrate this equation too, and tau, this is something I've already integrated. So it doesn't matter if I'm talking about I or F right now. So I have some I naught that leaves the surface of my star. And then I have all of this stuff that my photon has to get through. And so if you think about this as a stream like traffic, a stream of traffic, well, they're photons, but there's exit ramps all over the place, and photons go other places. So then when I'm left here, my screen is a lot smaller. So we're talking about how is it that photons get ejected from this path. Let's talk for a second about how to use this. How do I use this? So one particular problem that I might give you is I have, let's say I've got a G star. I got a G0V. V means it's a main sequence star, and the 0 is a subtle tweak on its mass. G is the important number. G and V really are the important bits. What's the temperature of a G star? Well, we can look that up. They're like 5,000 Kelvin. Okay, so now I'm going to observe a G star, and because it's a G star, if I measure its brightness, I know how far away it is, right? Because it's a G star, I know its temperature. Therefore, I know its luminosity is A sigma T to the fourth. That's at the surface. Then I know its absolute magnitude, which is minus 2.5 times the log base 10 of L over L naught. So I can get its absolute magnitude. And then I can get its apparent magnitude. Its apparent magnitude, little m, is big M plus 5 log base 10 of D over 10 parsecs. That's quite a fun. So in principle, all I need to know is what type of star it is and its apparent brightness to get the distance, right? Does that make sense? Does everybody see how I can do that? Let me make my screen lower so you're not peeking over it. But this doesn't always work because there's stuff in the way. So this works great. If this is all that I had, then I know the luminosity, and I know and I know the flux that I measure, but there's stuff in the way. So we also need to take into account the optical depth. So how do we do that? So let's talk about the apparent brightness is minus 2.5 times the log base 10 of D, L over L naught. Right?
That's absolute?
Absolute, sorry, yeah. The absolute magnitude is this, right? The absolute magnitude after I go through a cloud of stuff, so this is the atmosphere, it's not a big cloud of stuff, it's only about the size of the star itself. After I go through all this stuff, L is going to be I got too many L naughts. Let's call this L1. L1, I'm going to call this L1, times e to the minus tau. So this is the light that I get were it at 10 parsecs and went through a cloud with optical depth tau. So then how would that affect what my apparent brightness is? Then my apparent brightness is going to be little m. So how does this affect this equation? Let's talk about this equation. So then big M, we'll call this big M prime, is minus 2.5 times the log base 10 of L times e to the minus tau over L naught. I can just take this out, and this is equal to minus 2.5 times the log base 10 of L over L naught. This is just the magnitude that I had before. Minus 2.5 times the log base 10 of e to the minus tau. Does that make sense? So, if I'm looking at an object and I measure its apparent brightness as something, so let me continue this. M equals minus 2.5 times the log 10 of L over L naught minus 2.5 times the log base 10 of e to the minus tau. This I could do, this tau just comes down and becomes plus 2.5 times log base 10 of e times tau. this is a number, it's like 1.09. So then my apparent brightness, M, is going to be big M plus 5 log 10 of D over 10. We've done that a bunch of times. Plus 1.09 times tau. Tau is a function of frequency. I'm sticking that on there for a second. Okay, does that make sense? Yeah.
Is that first negative 3.5 log 10 of L, is that L1?
Yeah, this is L1. So this is, L1 is sigma t to the fourth. So that's what we get from the basic physics. You good? Yeah.
L1 is,
Big M or U M?
This is big M.
Oh,
L1 is sigma t to the 4th?
Yeah.
Sigma t to the 4th?
Yeah, L1 is what we get from physics.
Is
Yeah.
that like big M with the atmosphere?
Yeah, let's call this big M prime. That's what I call it over here. This is the absolute value, this is the absolute magnitude, also a cloud of crap in the way. Don't worry about the atmosphere, we just have some crap in the way, whatever the crap is.
Yes.
Right. So don't worry too much about star versus atmosphere. This is a thing that is radiating like a black body, and then a cloud of stuff. Just think about it. Yeah.
that's not, the underlying term, that's just, it turns into that 1.0.
That's right, that's right.
Okay,
Yeah, this becomes,
okay.
yeah. Did you have a question?
Yeah, one more here.
Okay. If you don't get there, let me know. So the effect of optical depth is to make things darker. How do I know it's darker? Because I'm adding a positive thing to my magnitude, right? Bigger numbers are darker. Okay, keep that in mind. You're gonna need this process. If you didn't understand any of this process, that's why we record the video. Or you can ask me, there's a homework problem that looks a lot like this. It's inverted. I ask you for what the column density is given the distance to a cloud and its apparent magnitude that is not what we expect it to be. Oh, sorry. I just realized that I had a great homework problem that I didn't put in the assignment. It's a good homework problem too. So the homework problem, I'll just tell you what it is. The homework problem gives you an HR diagram. And it tells you go look up formula on this HR diagram. Its visual extinction is given. What is its distance? It's very simply stated, has a lot of meat in it. Yeah.
That 1.09 tau term, shouldn't that be negative for the low end? Because you go from positive and then you put them over. Because doesn't your negative 2.5 log 10 L1 over L naught turn positive? And that's your thing?
I just swap M with M prime.
Oh.
I just stick in the magnitude that I actually have there. Yeah, so good, that's an important question. So I didn't reshuffle, I plugged in. Because they both distance and opacity make the brightness lower. So they both come in as positive numbers. It's a good question, thanks for thinking. So anyway, that problem isn't there, but it's a good problem. What's next? Okay, Rosslyn mean opacity. So this Rosslyn mean opacity is a number you look up in a table. That's all you really need to worry about. Because somebody went through the headache of actually calculating what it's supposed to be. But I need to tell you what it is because you're going to hear it and you're going to be like, what the hell is the Rosslyn mean opacity? At some point in time in your career as an astronomer. So, okay, a spectrum, the actual, let's pretend that everything's flat. Right? This is what my stellar spectra looks like. It's actually on a curve, but I took the black body part out. I have some mean continuum that the sun is making, and then I have holes that are punched in it by all of my elements. So this hole, and this hole, for instance, are helium lines. So this is helium 1, this is helium 1, this is the, let's say this is the passion alpha line, this is the passion beta line, this is the helium 1 bracket gamma line, whatever. So we have all these lines that come from different transitions in different elements. So I've got hydrogen and helium, and I have all of these different transitions in hydrogen and helium. There's a lot of them, and it's complicated, and it's a mess. And the opacity, kappa, is going to go something, is a similar ratty mess. It's not a thing I can do integrals over because they're gross. These are horrible functions. Each one of these has some shape to it that's really horrible. So we define the Rosslin mean opacity as the integral over wavelength of, okay, this is actually the inverse of the Rosslin mean opacity. It's the integral over wavelength of 1 over kappa nu times dB dt, where B is a black body, over the integral over d nu dB dt. Okay. Do you recognize this as a weighted average? Do you see why I would call that a weighted average? I'm averaging 1 over kappa, and I'm weighting it by the slope of the black body. You can tell that this is an average because I'm then dividing by the same thing. That's the sum over the slope of the black body. So this is the integral over q times w divided by the integral of w. So this is just adding everything up and then dividing by the number. It's just taking an average.
What is the subscript on kappa?
Nu, that's a nu. So this is my kappa that's a function of frequency, and it's this ratty mess that has all these level transitions, and it's all complicated, and some things look bright, some things don't. The average is the average of the kappa nu. This is not a function of kappa, of frequency. One of the useful things that we have found is that the Rosslin mean opacity goes like some number that you look up, somebody smarter than me, somebody who has a lot more time and focus and ability to deal with very little details, went through and said, okay, what's the average of this? It looks like this goes like some number times the mass density times t to the minus 3.5. This is called Kramer's rule. So what's the upshot of Kramer's rule? What happens to a cloud of gas as the temperature goes up? Can you see further through it or less far? This is a test that's going to be in the final, that next venture. Right? Okay, say it again. Temperature goes up. Can I see further or less far? So the opacity, so the temperature goes up, so the opacity goes down. The opacity goes down means there's less stuff kicking out photons so I can see further. Does that make sense? I heard you.
Stupid question.
Mhm.
Why doesn't that wouldn't that mass weighted average just be 1 over, doesn't it just end up being 1 over kappa?
No, this depends on
Oh,
frequency
because
too.
that's a different thing. I missed the subscript on the B.
Yeah, and these are the same thing.
Oh, no, never mind then. there's
So your
like this-
question still stands, right?
Question still stands.
This is a function of frequency, and it's inside the integral.
Oh, it's inside the integral?
Yeah.
Okay,
That's how it works.
that makes more sense.
Yeah, then
And the Rosslin mean opacity for K, is that a kappa with the
That's a
bar,
kappa.
kappa bar? Like capybara.
Yeah, it's like capybara. That's my favorite dog is a capybara. It's named Spoon.
Their dog?
No.
No, there's a superhero called the Tick who has a pet dog called Spoon. That's actually a capybara that got launched at him by Aztecs. Anyway, you guys all need cultural diversity.
Excellent.
Huh.
I'm kidding. It's from a cartoon from the 90s.
That was such a sentence.
Yeah, I know. Right? Okay, Rosslin mean opacity. The important thing is this. This is really what I want you to take away from this, right? is Kramer's rule. Rosalind mean opacity is messy, and we're not really. It's just that's a thing you look up, right? Somebody with time on their hands and focus, who is either more or less neurodivergent than me, or both ways will get you there.
Happy medium.
It's, I'm at the happy, not quite as useful medium. Okay, so this is the important bit, though. The opacity tends to go down with temperature. That's the important bit. Yeah.
Is that T to the negative 3.5?
Yeah, that's T to the minus 3.5. That's the important bit. So as temperature goes down, why does opacity go down as temperature goes up? Think about Boltzmann and Saha.
They're moving faster.
High energy.
Oh, that wasn't it.
Oh, so there just
completely
happens to
stupid?
be more.
They're moving faster, so what happens? More energy.
More energy.
What happens
so
when faster things move into each other, bounce into each other?
They have-
light.
They get more excited,
Yeah,
right?
they get more excited.
So all my things are excited outside of the place. All of my atoms have their electrons kicked out of the place where they're going to do the absorbing,
Oh.
right? So I have a line here because there's an atom here. There's a helium atom here sitting with an electron. Let's say this is the 3 to 4 transition. There's an electron already in the n equals 3 state. So when there's an electron in the n equals 3 state, then I can absorb the n equals 3 to 4 photon, right? But when I heat it up and then there's no more of these guys, then I can't absorb those photons anymore. Black.
Sorry, stupid question, but what does opacity exactly mean? Is it how much you can see or how transparent it is? What is opacity? So,
That's opacity. This is number of photons. And I'm not just saying it this way to be a smartass. I'm saying it this way because I want you to be able to get from the definition to the answer to your question, right? So, this is a differential equation, right? So this says how many of these guys survive, and kappa comes in as a negative. So kappa is how much gets kicked out. It's the loss. This is a bigger number, then this bit is more negative, I lose
Yeah,
more
so
photons.
opacity goes down, 'cause opacity is-
So
that's-
opacity is how much you can't see through.
Yeah.
Chase.
So,
So, no, you go.
so, if you have like,
Yeah.
say like you just have a bunch
Yeah.
of ionized electrons in the air,
Uh-huh,
photons are going through it like a star,
uh-huh.
they're bound to hit some of those ionized electrons.
Yeah, that's right.
So is that, like, they just gonna scatter elastically? off
Some of the time, yeah, so what can they do? They can either Thomson scatter or Compton scatter. Probably gonna Thomson
Well, so
scatter.
they can turn into other,
Usually not. They can change wavelength a little bit if there's Compton scattering, but usually that doesn't matter. And it never gets Compton scattered into the line of sight. So scattering, the photon leaves. Goes in some other direction.
what do you mean it never gets scattered? Oh, because
Oh,
it has
so
to
I've
change
got,
direction.
here's me, and this is my line of sight. It's actually very narrow, is the line of sight between me and the star. If I have an electron here, the odds of me having a photon that gets kicked into my line of sight is very small versus a photon that gets kicked out of the line of sight. So nothing gets kicked into the line of sight. But if I have just free electrons, then they'll get scattered and sent elsewhere, and they'll wander around. Eventually they might leave. But they're not gonna leave on the path that goes to me. So, other questions? We good? All right. That generated a lot of questions, so that was great.
I don't know what opacity meant.
I know, yeah.
Was that?
I thought opacity meant like transparent. That's like the more opacity it has, the more transparent it is. But it's
Yeah,
like the inverse.
it's the other way around.
If you think opaque means you can't see.
Yeah.
Opaque is
So
black.
opacity would be measured as you can't see how much you can't see through it.
So if you've got like the opacity knob, if you've got like Photoshop or something and you have the opacity knob, opacity high means black and opacity low means clear. But so there's an important question. It's important that we all have that.
Full grasp on the concept.
Yeah. Oh man, I have Sorry, I just came up with a great homework problem, but I'm not gonna.
Oh, you should totally show it to us before you put it on.
Well, unfortunately, it's a coding problem, and we're almost done with the coding things. So I'm not gonna write new coding homeworks. Okay, let's see, where are we at? What's the time? Effective temperatures. So, okay, how much time do I have? 20 minutes. I had 12.
23.
I ended 2:10, right?
Yeah.
Yeah. Okay. So I got two ideas that I want to get through.
2:30.
Yeah. Nobody's doing anything after this. Okay, so I got two ideas that I want to get through real quick, and one of them's pretty straightforward, but actually not straightforward, and the other one is we'll take a minute to get our heads around. So the first one is, what is temperature? So I have these nice things. More importantly, how do you measure temperature? That's the important thing. Because I don't necessarily care as an astronomer with a telescope about what temperature is in a philosophical sense. What I care about is what can I measure. So when I define these temperatures, we're going to define temperatures based on how I can measure it. So I have an effective temperature. So the effective temperature is what I get if I measure L equals A sigma T to the fourth. That's the effective temperature.
Is that related to Boltzmann?
No.
No.
This is related to Stefan Boltzmann. So this is the Stefan Boltzmann equation.
Sorry.
They're all related to Boltzmann
He did
because
everything.
he did all of these things.
He did all of them and it makes it very confusing.
Yeah. So this is Stefan Boltzmann.
At some point, you just need to start calling it equation 1, 2, 3, etc. So
Boltzmann
it's
one.
Well, that's why I
Boltzmann
call
on
him.
it.
Yeah, that's right. Which Boltzmann do you get to use? Okay, so this is a total tangent, but squirrel brain. I read this fantastic introduction to a statistical mechanics book, and it says Ludwig Boltzmann developed statistical mechanics.
Oh,
He died by his own hand. His student Clausius also died by his own hand. Now it is our turn to study statistical mechanics, which is pretty fun. Anyway, so statistical mechanics is challenging, but it's not so bad. Like, once you get used to it, it's pretty fun. So we have the effective temperature, which is this. This is all of the light. So this is kind of, in a way, one of the temperatures. We have the excitation temperature. And this is measured by N2 over N1 equals G2 over G1 e to the minus delta E over K T. I got to the T part. So if I can measure N1 and N2, G1 and G2 I know, and E1 and E2 I know. So that I know because I actually have a bottle of helium and I can screw around with it, right? So I can measure these things. It's pretty straightforward. So how do I use the effective temperature? Well, I just measure the luminosity, and that gives me the temperature. How do I measure the excitation temperature? Well, so there, I got to use a spectrum. So there, I have two lines, right? So I have these two lines, and so I have F2 and F1, and from some business that I'm not going to worry about at the present moment, from the fluxes of these two lines, I can get the ratio of how many elements I have in that line, right? So I know how many, so let's say that this is helium in the n equals 3 state, and this is helium in the n equals 2 state. I can get the ratio of these lines and get the temperature from that. Does that make sense? This is very, very important because this is one of the primary ways that we actually can measure temperatures. You can't use this to measure temperature because it's involved with too many things that are confusing, like the distance and how much shit is in the way. So this isn't that great to find the temperature, but this is really great because the ratio of the lines, all of the garbage that's in the way, the distance, all of that cancels out because of the distance, the reddening, all of that stuff affects these two lines the same. So the excitation and temperature is very, very important. The ionization temperature is a similar thing. We use Saha equation for that. And what does Saha say? Saha says that Ni plus 1 over Ni is 2Zi plus 1 over Zi. This is the partition function. I'm always going to give you the partition function. You're never going to need to compute the partition function unless it's for something like hydrogen, where you know that the partition function is 2n squared. For the most part, I'll give you the partition function. Or it's 1 for a free particle. So this partition function, a thing that goes like the wavelengths, and then E, the minus ionization potential over KT. So there's a squiggle in here because I don't care about that part. What I care about is the T up here. So we can get the ionization temperature by looking at how ionized the lines are. And similarly, you get that from a spectrum. So this line is a neutral hydrogen line, and this one is a neutral helium line, and this one is an ionized helium line. So from the ratio of these two lines, I can get the temperature. Okay. There's the kinetic temperature, which we get from the velocity distribution. So we know that n of v dv equals v squared e to the minus v squared over kt dv. We'll put this in quotes because I know I'm missing some numbers in there, but they're not numbers that I care about. They're numbers that I sometimes care about, but it's not the functional behavior. So n of v goes like v squared e to the minus v squared over kt. The t is up here. It's the width of the thing. And then the color temperature this is the slope of the Planck function, which I'm not going to write down all the way. So we have these different ways to measure temperature because we have these different processes. And if everything is in thermal equilibrium, then they ought to give you the same answer. Sometimes they don't, and if things are not in equilibrium, then they're not going to give you the same answer. So if things are exploding, then you're going to get different answers from all of these. So these are how we measure temperature as astronomers.
So in equilibrium, they're all the same?
Principle. But then you got to measure it. So if I measure, in principle they're all the same, but my measurement uncertainties are going to be different for every one.
And how do you measure the effective temperature?
Well, the effective temperature is really hard to measure. You got to measure the luminosity and the surface area of the star and the distance to the star. So you got to get all of the things. So it's harder. So the effective temperature is the one that's maybe used most often because it has this beautiful relationship, but it's also very difficult to get. The color temperature is easier to get because you only need 2 points of the black body. These really ought to give you the same answer because they're coming from the same function. But again, they're not necessarily going to give you the same answer because your measurement uncertainties and all these things are different for different things. Okay, does anybody have any questions about excitation temperature? Yeah.
For ionization, is that exponential negative?
Yeah. Yeah. Don't write this down.
Oh.
Go look up Saha. I was being sloppy there. I just wanted to get the bits that I care about. The bits that I care about
Okay.
is the e to the minus chi over kt.
So just remove that and just go look up Saha.
Look up Saha for that. Okay. The last thing I'm going to talk about is line widths. Because this is this kind of strangest thing. So in quantum mechanics, everything is quantized. So when I have a hydrogen atom in the n equals 4 state, and it goes to the n equals 3 state, then I get a very well-defined photon. right? So here's my hydrogen. Here's n equals 3. Here's n equals 2. This looks like this. So here's the ground. Let's call this 1. Here's n equals 2. N equals 3. So the photon I get is going to equal, so the frequency for the photon is just going to be the energy over h. I'll throw C there. The frequency of the photon is just the energy of the gap over h. And the energy, we said, is minus 13.6 times 1 over n squared. But we also said that delta x, delta p has got to be bigger than h. I think it's h bar over 2. And also delta e, delta t has got to be bigger than h bar. I think over 2.
Or equal to.
It's never equal to. Yes, formally. But equality is never really actualized. So what does this say? This is the important one.
Uncertainty.
What's that?
This is a Schrodinger, or not Schrodinger, Heisenberg.
Uh-huh.
Uncertainty?
This is a Heisenberg uncertainty,
Okay.
that's right. So this says that the uncertainty in the energy times the uncertainty in time has got to be H2. What does that really mean? That means that if I'm an electron in this energy state, I'm going to have 13.6 over 4 electron volts of energy, or I could have 13.6 over 4 EV plus delta E. I could have a little bit of extra energy, but how long can I have that little bit of extra energy for? Not very long. It's going to be delta E. It's going to be H bar over delta E. So I can have a little bit of uncertainty, but the uncertainty only lasts for a little bit of time. So a bigger uncertainty can last for a littler time. So delta T has got to be bigger than or equal to H bar. Let's just call this H bar for now, because that too doesn't really matter. Over delta E. So my electron can be real high energy relative to other n equals 2 electrons, but not for very long. Only for a time span that is given by H bar over that energy. So I can be a real far away, but really not for very long. Does that make sense? This is in a lot of ways, well, I don't know, I'm not going to say that. I was going to say this is more important, but it's not really. This is very important. So that means that this energy state, so that means that there's some error in this energy that's caused by quantum mechanics. And so you can sort out that delta lambda is equal to lambda squared over 2 pi c. Actually, don't write that down yet. I think that's a plus. No, come on. So the width, did I write everything down? To h, oh, I missed an h and not a pi. Turn my pi into an h. That's. So what does this say? This says that the width of the frequency is going to be equal to the error 1 over the time that it could be in these odd states. Or you say a little bit, or you can say delta lambda equals lambda squared over 2hc times 1 over delta t naught, where delta t naught is the lifetime of that state. Because really, an electron is only gonna park in this n equals 2 orbital for a little while before it falls back down to the ground. How long that takes is this delta t naught. So the width is kind of how stable is this platform, yeah.
I'm pretty sure the reading said it's, with 2 pi c instead of 2 h c. That's what I have in the notes for the reading.
Well, it's your notes versus my notes,
Okay.
and I'm totally spacey. So my notes aren't trustworthy,
Mine are neither.
Mine says pi.
but so it might be a pi. All right, let's leave that as a squiggle. Once again, things I write on the board have error. Sometimes I didn't write them down well enough because I can't do I can't do all the derivations in my head. I'm pretty sure there needs to be an h though because it's quantum mechanical. But regardless, look it up in the book if you actually need it. Oh, this one's a pi. I have a pi for that one, and not a 2. Regardless, the physics is the physical process is the important bit. The physical process is that there's some width to this state, and depending on how wide the state is, no worries, you might get some broadening. So the broadening looks like this. He doesn't say this in the text, but I'm gonna. The wavelength actually looks like b over. Is there a pi? There's always a pi. There's always a pi.
Always off by a factor of 5.
I spend my entire life chasing a factor of 2 pi.
There you go.
Yes, there's a pi.
Stop
B
listening.
over pi times lambda minus lambda naught squared plus b squared, where b is it's the half width of the thing, and it comes from math that I'm not going to get into. The important bit is it goes like 1 over lambda squared plus 1. Where then you got to rescale it for the actual physics. So it's going to be b over lambda squared plus b. And the lambda naught means, okay, this is centered around some lambda naught. So what this profile looks like is here's lambda naught. That's what the quantum mechanics gives you. This is centered like this. So now the other broadening that we get is thermal broadening or Doppler broadening. There it is.
This is the like normal broadening, like a nat.
Yeah, they call this natural broadening. I would call it quantum mechanical broadening, but natural broadening is fine.
Yeah, if they do, so that's caused by the quantum mechanics.
Yeah.
Okay, because they didn't clarify that in the book. It's just called natural, and I'm like, there's a lot of natural things I don't understand.
Yeah, this is quantum mechanical broadening. And he doesn't say this. This is the Lorentz. And he doesn't really need it, but that's all right. So the other broadening, let's talk about pressure broadening really fast. The other broadening that's weird is pressure broadening. And that yeah, this is basically, so you get a similar kind of I don't have an H there. Anyway, C pi 1 over delta t. You have a similar kind of formula where delta t is now the time for an atom to get kicked around by another atom. So you've got this sea of atoms, right? And they're all bashing into each other like a mosh pit at a metal concert, right? So they're all smashing into each other. But it's not really like a mosh pit at a metal concert, because in a mosh pit, everybody's pretty close together. This is like a mosh pit in a huge open field where you run for half a mile before slamming into somebody. But there's so many people you're in.
Socially distanced mosh pit.
Socially distanced mosh pit, I like this. So this delta t is how long they're hanging around for, and that comes from the velocity of the atoms. So the velocity, the most probable velocity is 2kt over the mass, square root of that. So we get a similar kind of formula. So this looks like Yeah, lambda squared times n sigma over pi times square root of n k t over m. Okay, that looks better when you read it in the book. Pressure broadening gives you a profile that looks like this, is because the atoms get kicked around by the other guys nearby. Doppler broadening. Okay, so for what I do professionally, I worry about Doppler broadening a lot more than the other kinds of broadening because I deal with big clouds of gas that are ultraviolet because they're near supernova explosions, but they're very low density. So Doppler broadening is very important. So Doppler broadening. So if I have, so this is a flux versus wavelength. I have with no quantum mechanics, my line is infinitely thin and at exactly one frequency. So because of velocity, the velocity of the particles coming at you, I could have, some of them could be over here, some of them could be over here. So I get my wavelength for Doppler broadening, the wavelength is, where are we at? Sorry, 2 lambda over c times 2kt over m, square root of that. So this is just the velocity of the gas. Why does this work? This works because delta lambda over lambda equals v over c. You should tattoo this onto your forearm or something. Make sure that this makes sense to you. This is the Doppler shift formula. Delta lambda over lambda is v over c. So I just move this lambda over here, and I'm left with this.
What's in the denominator and the square root?
M, that's a mass.
It's an m? Okay.
Yeah. So 2kt over m is the mean velocity, is the most probable velocity of a particle in a gas with temperature T. 3kt over m is the average. So the most probable and the average are different. But this kt over m, square root of kt over m is a means of velocity. So when you see that, you should say, oh, yeah, that's a
It's
velocity
the most probable velocity
of a Maxwell.
oh,
So now I have the thermal motions of my particles, and then I have actual bulk motions of my particles. The cloud of gas could be actually coming at me at 50 kilometers a second. That happens. So in that case, then delta lambda is going to be 2 lambda over c. Square root of all this jazz, I got 2kt over m plus the thermal velocity squared, or the bulk velocity. The turbulent velocity squared. And this is a Gaussian. So pressure and natural broadening give you a Lorentzian, and Doppler broadening gives you a Gaussian. And a Gaussian looks like this. Gaussian is narrower than a Lorentzian. And I'm going to have both of those processes. A lot of times, if I have like one of these star-forming clouds, have you guys seen the Pillars of Creation? One of these star-forming clouds that's real violent, the temperature's real low and the kinetic energy is real high. So you only see the Gaussian, but in something like the atmosphere of the sun where the temperature is real high but the velocity is not real high, you see mostly the Lorentzian. Did you have a question? Or were you just, was that? Okay, let me know.
what is the turbulent velocity?
This is the velocity of the turbulence of the cloud. So that has some kinetic energy from just bulk motions of the cloud. So when I add a Gaussian plus a Lorentzian, this gives me a voice profile. I can no longer use that chalk. It has come to the end. And the void profile is a sum of a Gaussian and a Lorentzian, which means we're summing up the Doppler and natural terms. All right. So okay, that's I think all I got for today. Does anybody have any other questions that they want to talk about? One more? Yeah.
Why is there two in front of it?
I wouldn't worry too much about that too at the moment. It might be a typo.